So, let us start with our second session today. I hope you guys were not tired. And this second session today is about consistent PLS. Okay, when we talk about this consistent PLS, um, just to explain to you, I uses consistent PLSC. I published before PLSC, but I rarely use PLSC because of certain condition that some of my mentors that taught me and told me that really you want to use consistent PLSC. So yeah, because of that, again, I'm not trying to say consistent PLSC is no good. I'm trying to say that our users, my colleague and I have published PLSC together. I think the paper was in 2016 under International Journal Business and Society. It is a UNIMAS journal, Scopus. And that time I was a very new scholar, young scholar. So we have published together with my colleague together. We uses PLSC. But again, throughout my entire journey, I rarely use PLSC for research due to certain issue. But again, I'm going to explain about PLSC. Okay. So before we talk about PLSC, we need to know the basic about the estimation used in PLS-SEM. Back to the most fundamental, when we talk about PLS-SEM, we always estimate our model composites, okay? Composite estimation. And this composite estimation can be mode A and mode B. A traditional way of saying mode A and mode B is like, when we talk about mode A, is like a when you use reflective construct. When you talk about mode B, we talk about formative construct. But if you look into Becker, Rye, and Rigdon 2013 and Rigdon 2016, they have mentioned clearly that even in your informative stage, you also can use that mode A. It is very interchangeable in this estimation because in PLS-SEM, we are talking about composite rather than really focus on the term like reflective formative. We always mention about mode A and mode B. But on top of that, when we have the CB-SEM, which is the Amos world, or maybe least real or M+, we always have another type of estimation. We call it as common factor model. And this common factor model was first captured very clearly by Dijkstra and Henselaar 2014 in organization research. I think, no, it's Dijkstra Henselaar 2015. I have written wrongly, 2015, mentioned clearly that there's a way for PLS to look into the common factor model world. And this common factor model world uses another terminology called the PLS-Consistent, and some we call it as consistent PLS. The purpose of this consistent PLS is to reduce the PLS bias. This is what they have been highlighted in their literature by Dijkstra and Henselaar. What bias is Dijkstra and Henselaar mentioned? I'm going to explain in a short while. But again, the purpose of PLSC, before we want to understand this PLSC, I would like to get into the most basic way of doing research. The most basic way of doing research before we plan to use an algorithm to run our analysis is we need to make sure there are 4 types of way of modeling. Whether you are focusing on confirmatory research world, explanatory research, predictive research, and auxiliary research. But back to the most fundamental, when we use the traditional PLS to run analysis, most of the time, we are focusing on the combination of both explanatory research as well as predictive research. We combine the best both worlds of these 2 techniques into our modeling. But when we are seeking for pure confirmatory research, then therefore we have our covariance-based SEM, Amos, and PLS. The last but not least is auxiliary. Auxiliary here is about if you plan to do something like proxy in terms of your concept, especially you use the secondary data, you study about performance, sales, profit, ROI, ROE, then that's another way type of modeling. But right now, I'm focusing on the first one, which is the confirmatory research. But when I explain this confirmatory research, I'm not telling you whether you must use PLSC or not. What I explain to you here is the purpose, and you as a researcher, you need to think twice to use or not to use. Because I'm not who to tell you to use it or not. Because right now, the PLS world is getting more confusing, where we have the CFA, the CCA, And now CCA, we have two debates on different way of looking confirmatory composite analysis. So I'm not going to debate on that, because although I know what's happening around, but I'm not going to debate on that because I'm not in that league to debate. This is up to the top PLS researcher to debate. But today, in this PLSc, I'm just explaining confirmatory research modeling. Okay, so back to the most very fundamental of confirmatory research. In PLS-SEM, we also can perform the factor-based PLS-SEM, and this is somehow similar purpose with the covariance-based SEM. And it was first developed by this person, Theodystra and Henseler, 2015, and their belief is also the same, where if you do a reflective construct, okay, reflective construct, okay, and this reflective construct, I will explain more detail what they think about reflective. Okay, so when we talk about reflective construct, it's always, most of the time, is like behavioral perception study type of concept and construct that we use in our social science research. So therefore, when you do this type of when you use this type of construct, which is perception, behavior, we look into actually pure factor-based way. Okay, the pure factor-based way is just explanatory without prediction. So when we talk about pure explanatory, it's like x to y, x explained to y. Therefore, at the end, we need to look into the divergence between empirical covariance matrix as well as model implied covariance matrix. And this fundamental purpose itself is come from covariance-based SEM. So what is this? Okay, to explain this in a simple way, what do you mean we want to look into the divergence? Which means that we want to minimize the difference between empirical covariance matrix as well as model implied covariance matrix. Okay, bear in mind, I give you a very simple scenario. Let's assume that empirical covariance matrix are based on the sample that you collected. We call it sample covariance matrix. And model implied covariance matrix, that it is assumed based on theory. If a theory said that X lead to Y, then your data must say X lead to Y. So model implied covariance matrix is more about the theory. For example, we talk about theory plan behavior. When we talk about theory plan behavior, we always know that attitude, suggestive tone, PBC lead to intention. And this is a theory which is like, you know, it's been there for so long. So right now we go and collect sample. Okay, the sample will be empirical. So model, which is your theory, empirical is a sample, and right now we want to see what is the divergence between the theory said this way and the sample said this way. We want to get small divergence. We want to minimize the divergence so that you will move into a confirmatory purpose, that your model can be confirmed based on the data that you collected. So in a very more layman scenario, is like, if the theory said like the earth on the left-hand side, as you can see the picture on your left-hand side, this is the earth. The earth said that the theory looks in such a way. Then you go and collect your sample, and you collect your sample, and at the end of the day, when you collected your sample and you run your model fit, and your data does not show really that the earth looks like on your left-hand side, but your earth looks like your right-hand side, then it somehow said that your model does not fit. So this is a bit some scenario and the purpose of factor-based, regardless PLS-SEM and CB-SEM. But in PLS-SEM factor-based, we are talking about PLS-consistent. So this is the first fundamental you need to know regarding the factor-based world. So it's like what I mentioned, we have empirical from the theory, and then we have implied, then we run analysis. We want to see the discrepancy. When we talk about the discrepancy, we want to see how close the discrepancy is. The closest the discrepancy, the smaller the discrepancy, it shows that your model fit and you can confirm your study. Okay, so but to be more detailed, we need to also understand, besides the algorithm, the purpose of factor-based, I was mentioning just now about reflective. When I talk about this reflective, there are two ways of seeing things. One, reflective can see it in the common factor model. The other way of seeing reflective will be a composite model. Okay, as you can see A and B, okay, just look at the diagram. Don't need to look into the words, okay? Or yes and no, do not need to look. Look into the diagram. If you plan to do a factor-based, okay, a pure factor-based, covariance-based, pure factor-based reflective measurement, it will look like your A side. The A, figure itself clearly shows that this is the true way of doing reflective. And this is what we call a true reflective, okay? A true reflective where it look into common variance, okay? Common variance, okay? Common variance. But when you look into the traditional way of doing PLS, it is called the composite measurement. When I talk about composite, a lot of researchers confuse that composite is actually formative, okay? It is true that composite is actually formative, but this composite here right now I'm explaining is about composite estimation, not modeling, estimation. When I say composite estimation, it looks like number B, where your error is actually correlated and your construct and item can either reflective or formative. So right now, we are not looking into the composite type of reflective measurement. We are looking about the true reflective measurement. To run a true reflective measurement in PLS, we will use PLS-Consistent. I hope you are clear with this, okay? So to give you more detailed scenario, I always love to use this example by Sasted et al. 2016. They explain that a lot of people confuse with the term of composite, okay? But let us look into the most fundamental way. We have the theoretical layer, we have the conceptual layer, we have the operational layer, and then we look into the more bottom one, which is the measurement approximation. But let us look at the top. At the top, we have conceptual variable. Conceptual variables, we clearly know that when we want to use a construct or concept, we look into the construct and the variable itself, whether it is reflective or formative. And when we talk about reflective, when we look into the operational layer, reflective itself called effect indicators, okay? It is manifested, okay? Manifest from the construct to item. But when we look into formative, it breaks into two, okay? What we know is informative in PLS, we call it composite. And this composite, not composite construct. We are talking about composite indicators. And then we have another way of looking at it called causal indicators. To perform a causal indicators, what we always use in CB-SEM is like mimic modeling, where we have formative and reflective together for a construct. But we are put aside causal indicators here right now. We are talking about reflective conceptualization to effect indicators, as well as formative conceptualization to composite indicators. With these two effect indicators and composite indicators, we look down into measurement approximation. In measurement approximation, we have two terminologies that you need to know, whether we are looking to common factor or composite. If you are common factor, it is more towards CB-SEM world, as well as PLSc or PLS-Consistent. If you look into the composite modeling, and this composite modeling right now is estimation, nothing to do with the construct, it's estimation, we use the traditional PLS called PLS. So I hope you guys clear with these terminologies in terms of what is called composite indicators, what is called composite estimation. It is different stuff, okay? So from here, what I meant just now is like we are moving towards confirmatory world. When we are moving confirmatory world, put aside prediction, put aside explanatory, pure confirmatory world, we have two steps approach. If you use this traditional modeling, which is called composite modeling, we're gonna use, when we do a reflective construct, we're gonna use a mode A. But let us move one step further. If you plan to do into confirmatory, rather than just traditional PLS where you want to do prediction, we move into confirmatory world, then you want to do a pure CFA, then I could say that you need to do this attenuation using PA. PA means row A. This attenuation using PA is, in the end, to adjust your reliability into row A. Row A is a reliability value, a reliability criteria that used in PLS-Consistent. And this attenuation using PA is related to PLS-Consistent. So what does it mean? It will correct the correlation between two variables, okay? And it uses pure reflective construct where your errors are not correlated. Again, the errors are not correlated. But if you use a mode A in PLS, your errors are correlated. To give you another scenario, give you again an explanation, if you talk about using PLS-Consistent and you want to do a pure reflective, a true reflective, a confirmatory reflective, then will be your A figure. But if you plan to do like, composite modeling, okay? Composite modeling, and in composite modeling, you prefer look into prediction type of reflective way of doing things, then you will look into the B. And the B1 is the way of how we always do the reflective in terms of using SmartPLS software. But if you move into more advanced, you want to do a more confirmatory stuff of research in terms of your reflective measurement, then we are looking to PLS-Consistent, and this PLS-Consistent, we will look into the A figure, okay? As you can see on the left-hand side at the top. Okay, so back to this one, we have explained. So in PLS, when we look into the traditional way of doing PLS reflective, we always assume that when you run a reflective in PLS, we need to have, large number of observation as well as large number of reflective indicators. Why? This is according by Herman Wood itself, 1902. They have Herman Wood itself mentioned that if you want to do a reflective using a traditional PLS, like what we have always done, is like we assume that our observation must get a lot of sample size, as well as your construct, the reflective indicators must be large, so that your estimation of your reflective will be consistent as nearly like your PLS consistent. But in such a situation, Dijkstra 1983 mentioned that regardless you use a PLS estimate with large number of observation, large indicators of your reflective construct, it is still create an issue called loading will be inflated. Loading will be inflated is like if you use a PLS, sometimes your traditional PLS that produce reflective measurement, you have bias in terms of inflated loading value. That is what Dijkstra mentioned. On top of that, you're going to also face an issue according given 2011 that your path coefficient also will have bias. Why? It is not adjusted according to the true reflective. A true reflective is the common factor. Okay, so in such a way, Dijkstra and Seller have shown that if you plan to use a reflective construct and you plan to do a confirmatory type of research where you want to produce the true value of reflective measurement between two constructs, for example, IV to DV. For example, here, I do not want to talk about the grid symbol. I worry you're confused. Let's say the IV is on your left-hand side. Your DV will be N3 and N4, N2, okay? Imagine you have two correlation. And if you use a traditional PLS, you will have type 1 error. Why? You will have inflated value in terms of your path coefficient. Sometimes also you create deflated value in terms of your path coefficient. And that includes your loading also. Why? Because you correlate the error and uses a composite type of estimation. Therefore, Dijkstra and Seller assume that if you do a reflective, a true reflective construct must follow the CB-SEM concept, which is like your Amos or Lisrael, that your error should not be correlated. Your reliability of your PLS, traditional PLS, must be adjusted using rho A so that it will produce a true value of your path coefficient. And as you can see, the arrow that highlighted, if I use traditional PLS, it tends to be significant where the beta value is 0.19. But if you use a true reflective estimation, which is using the PLS consistent, it can get 0.00, which means no significant. And that's the reason where you could see sometimes you could have inflated and deflated value in terms of your path coefficient, especially when you measure on true reflective construct. So when we talk about this true reflective construct, I hope it will not confuse you that when you use a PLS consistent, the main purpose is to correct the correlation of two latent variables. And these two latent variables, I'm talking about IV and DV, and this IV and DV is reflective, okay? When I talk about reflective, I'm talking about true reflective construct. I will use a different terminology so that you will not be confused. True reflective rather than composite reflective, okay? I'm not talking about composite reflective. I'm talking about true reflective. A true reflective means you are trying to mimic Amos result of reflective. So I'm talking about correcting this in PLS. Therefore, this is the purpose of PLS consistent, where it corrects the correlation of two latent variables for their measurement error. So to correct this, PLS uses at first, PLS will run the normal traditional PLS to get the latent variable score, which is your original estimate to obtain the to obtain the disattenuation correlation. What do you mean to obtain the disattenuation correlation? Is to correct this correlation from the old traditional PLS score. And then by dividing the latent variable correlation by the geometric mean of the latent variable reliability. What does it mean? It means that look into the formula Rij. R stands for correlation, I mean maybe independent variable, J mean dependent variable. So we first produce the correlation of two variables, X and Y, which is the relationship. Then what you need to do is divide by the square root, which is the geometric mean of the latent variable reliability, which is rho, which is the P, equals to EI multiplied with another P, latent variable reliability of rho A. So you have two rho A, one is X rho A, one is Y rho A, which is the new reliability, which I'm going to explain later. So that is the formula to correct the correlation effect between two variables when you use a PLS consistent. To calculate the rho A, which I'm going to explain, which is the P, as you can see the symbol called P there, we look back into the traditional reliability coefficient. In the past, the traditional reliability coefficient, we have the Cronbach alpha, 1951, and we have the gyroscope P, which is called the composite reliability. The real terminology of composite reliability called gyroscope P. So as you can see, based on literature, Cronbach alpha tends to produce underestimate value in terms of reliability. But when we look into composite reliability, which is your gyroscope P, it is overestimation. Okay, so therefore, Dijkstra-Henselaar in 2015 proposed a new technique which could find the true reliability that lies between CA and CR. CA mean Cronbach alpha, CR mean composite reliability, and this reliability called rho A. And in this rho A, it will produce accurate result of reliability which mimic Amos result, or mimic covariance based result, or mimic Lisrael or M+ result, which means it will produce the true reliability value as close as what we call the true reflective. Okay, I hope you understand this. And then to calculate this rho A, which is called the PA, we use the formula of outer weight estimate, which you can see W called outer weight estimate. Then you will divide by the sample covariance matrix, which is the S there. And then it will produce the consistent reliability. And this consistent reliability we call PA, some we call rho A. Okay, so I hope you understand. If you don't understand the formula, never mind, but you need to understand the formula so you understand how it calculates this rho A using this formula, using sample covariance matrix and outer weights estimation. And from that itself, PLS, since the purpose of PLS consistent or consistent PLS is to correct the correlation between two variables, which is X and Y. So therefore, it follows 4 steps of formula. First, if it generates traditional PLS result. In traditional PLS result, the main purpose is to calculate correlation between two variables and get the latent variable score. And this latent variable score can easily done in PLS algorithm iterative software program. But then when we move into step 2, things getting more fancier, where once you get the latent variable score, the second step itself for consistent PLS is to calculate the rho A. In rho A, the calculation is only for reflective latent variable. If you have mixed model such as, mixed construct, such as you have formative, reflective, or maybe you have single item construct, then all will be set to 1 if you have formative or single item. But for reflective, they will recorrect back the rho A using the outer weight estimate as well as sample covariance matrix, as you can see in the formula here using the PA. And then when we move into the third step, it starts to correct for attenuation. As you have seen this formula below, which is Rij, which is the correlation of XY divided by square root of rho A reliability first construct as well as the rho A reliability second construct. This itself will then be a good step itself that it correct the inconsistent correlation matrix of the latent variable score obtained in step 1, which means it corrects the correlation matrix of the traditional PLS from the reliability that generated in step 2. Okay, this reliability generated in step 2 will be your true reliability of represent reflective construct. And then we move into the fourth step itself. In fourth step itself, the consistent correlation matrix of the latent variable score allow re-estimating all model relationship yielding a new consistent value of path coefficient, R squared, as well as loading. In other words, when you correct your reflective, traditional reflective, which is using composite estimation, into a true reflective using PLS-Consistent, by having new reliability score, which is called rho A or PA, it will correct for attenuation so that it will then estimate a new value, which is the true value of the reflective of X to Y that represent CFA, that also represent a true reflective estimation. So that is a bit some, introduction, some formula regarding PLS-Consistent. So I hope you are not familiar. I hope you guys are not confused with the formula. But to keep it short and simple, I would not want to talk about this thing. Okay, I think I can briefly talk. Dijkstra Henselaar 2015 have run a analysis and simulation published in MIS Quarterly. They compare that running two construct X and Y, different loading, different loading, same loading with a path coefficient. It found that if you have a reflective construct, and according to Dijkstra Henselaar, if you really ignore, I use the word, that is according to Dijkstra Henselaar from his point of view. If you know that you're using a reflective construct, which you study about perception study or behavioral study, and you ignore using PLS-Consistent, you will get bias in terms of your loading value, as well as your path coefficient value, as well as your R square. And their simulation proven that using PLS-Consistent will produce a consistent result from the simulation of the true correlation value of 0.5. For example, a simulation study shows that a true value will be 0.5, but if you look into the right-hand side table, you have true correlation is 0.5, but when you compare PLSc and PLS, and when you run a model where you have two constructs that is reflective, the correlation estimate by PLS will get deflated value based on his simulation, and will have bias compared to the true value of PLSc, which get exactly the same value of a simulation correlation of 0.5. As you can see in the table on your right-hand side. And this is also similar with the rho A reliability, which is PA. And you can see the PA result of reliability get as close value as the true reliability. This clearly shows that from Dijkstra Henselaar study, if you really know and assume and feel that the construct that you use, which is reflective, and you are studying about perception study, and you know it is supposedly to be a true reflective, and you run it in PLS estimation, which is the traditional PLS, and this traditional PLS called what? Composite modeling, then your result will always get deflated value, sometimes will get inflated, and that creates type 1, type 2 error, especially when you measure X to Y, where you both itself is reflective. But when we move into the true reflective, where you run PLS-Consistent, it will mimic exactly the same result like your CB-SEM world, where when you have true reflective, you run the right estimation using PLS-Consistent, it will produce exactly the result that you want, which is the true correlation. And this is what Dijkstra Henselaar mean. Okay, so since with that itself, Dijkstra Henselaar have summarized that the parameter accuracy of the PLSc, and it stated very clear that PLS-SC and CB-SEM is the same. Especially when you know the construct that you use is reflective, and you know and you assume that it is a true reflective, then PLSc is actually equivalent with your CB-SEM, which means that for those AMOS users, sad story to you guys, that you do not need to use AMOS or M+ or Lisrael, because when you run PLSc, you get exactly the same result like CB-SEM. But again, PLSc will get more advantage compared to PLS and normal regression if you are talking about a reflective construct, which is a true common factor construct, or we call true reflective. But let us look into the statistical power. In statistical power, it is obviously that CB-SEM is equivalent to PLSc, which means PLSc could mimic AMOS result or CB-SEM results. And when we talk about type 1 error, PLSc would not have type 1 error like what PLS and regression does when you when you assume that your reflective is a composite type of reflective, it's a no situation in PLSc. But in terms of the convergence, whether you run the analysis, whether it works, because sometimes when you run in CB-SEM, you have problems in terms of running because of under-identify, over-identify, and so on. So CB-SEM tends to be got problem, but if you use PLSc, there's no convergence issue. Your analysis will definitely run. So that is the advantage of using PLSc, which stay in the middle between covariance based as well as PLSc. And that's the biggest contribution done by Dijkstra and Henseler 2015. Okay, so why use PLSc instead of PLS, the normal PLS? So my explanation is very clear. PLSc can handle models within more variables than observation. Compared to CB-SEM, as you can see, when you use CB-SEM, if you're AMOS user, you will know that if model too complex, you cannot run. Suddenly, out of sudden cannot run because the canvas is not enough, fit in, and a lot of issues, some more Haywood cases, and so on. So this is one problem in CB-SEM. Therefore, PLSc can handle a lot of variables. It can handle parameters than observation. It can even handle a model. We have formative endogenous construct. And when we talk about PLSc, it less affected by misspecification in model subpart. And PLSc does not suffer from convergence problem. You can easily run in PLSc. I think this also can be easily performed in PLS. That is the advantage of it. I think two software only uses PLSc, SmartPLS and PLS, if I'm not wrong. And PLSc can easily extended the handling of non-linear effect without any numerical integration. And this is easily can be done in SmartPLS software or PLS, PLSc. That's the advantage compared to CB-SEM software algorithm, like using maximum likelihood and so on. So this is the advantage of why people use PLSc. So I hope you get some knowledge about PLSc. But yeah, I'm gonna stop here for a while. I will show you all how to use the software on how to perform PLSc. Super easy. But before that, I will look into the questions. See you guys got any question. I will